Absolutely. Thank you very much. And thanks to BlackAlps, all the organizers and everything. I really appreciate the opportunity to be here. Like was mentioned, we're going to talk about some side-loading techniques that are relevant to .NET, so payload development. This talk is pretty like red team or pen testing oriented. But before we dive into it, a quick introduction of myself. I work at SpecterOps on the adversary simulation team. I've primarily been focused on red teaming and pen testing for the majority of my career. I have some interests here, as well as my Twitter handle, and also wanted to give a shout out to the co-creator of this talk who couldn't be here today, but Stephen Flores worked with me on this presentation as well. So a quick overview. I'm going to define some terms because when you say payload, that means something different to every person that you talk to. So we'll go through what that means as it pertains to this presentation. We'll talk about execution flow hijacking and some .NET specific execution flow hijacking, some additional opportunities that .NET Framework gives us in that regard. Then we'll talk about some additional relevant payload attributes, so runtime protections, modularizing some of these techniques, as well as compilation considerations. And then we'll finish up with entropy conscious obfuscation and automating this whole process. So a quick disclaimer about this talk. What I want this talk to be is a combination of several well-known techniques. The TLDR is nothing that's presented here will be entirely new and novel, but what myself and Steven and some other people on our team that make use of some of these techniques find the value in what I'll be presenting is that when you take these well-known concepts like modularizing your payload, taking special considerations when you're constructing how you want to do things like shellcode injection. When you take these well-known concepts and apply them together kind of like holistically, make sure you're checking all the boxes, then we have really good results. We don't need to do like triple backflips, indirect syscalls, anything crazy. We have a high level of success with some of these more basic techniques. So defining some core concepts, what payload is going to mean to me or us for this presentation is just what we're executing on a machine in the context of initial access, seeded access, persistence, things of that nature. So this could be a script that's interpreted. An example would be like combining the project gadget to JScript with VBScript execution to abuse WMI event subscriptions. Just simple application to be executed. So this could be part of like a click once deployment, things of that nature, or deserialization of a serialized blob. So like kind of recent, an event viewer related UAC bypass would be relevant to .NET deserialization. And also as we're creating this thing that will be executed, keeping in mind that we want this to be modular and replaceable in design, because at some point there will be some detection written for what we are creating. So making as much of what we're writing interchangeable, like at build time or when you need this for an assessment or some other type of engagement, you want to be able to like mix and match every piece of this payload. So a little bit about execution flow hijacking. We have our traditional approaches, which would be like DLL side loading, DLL search order hijacking, COM hijacking. So when we use the term like hijacking or side loading, these are some of the things that probably come to mind initially. There's a lot of overlap in these techniques. So like when people say side load or hijacking, these terms are often conflated. And I think based on my own research, what is meant when somebody says side loading or hijacking really boils down to the intent. So side loading is commonly associated with like bundling a malicious DLL with something that you want to achieve some sort of arbitrary code execution with. That's more in line with what we'll be talking about here. And hijacking is typically abusing like search order, the legitimate search order path. So there's a lot of differences in these traditional approaches. So what is coercing the hijacked flow of execution, for example? If we're talking about COM hijacks, this would be searching of specific CLS IDs, which registry hive it's coming from, for example. In DLL search order hijacking, an example would be like an addition to the path environment variable. But these differences introduce additional options in terms of how we're going to abuse these things. So like in the case of a COM hijack, when we're interacting with registry, from a like red team or pen test perspective, it's really important to understand how we're interacting with these like operating system internals to know what might be more likely to be detected, what might not, maybe take a less standard route. So if we're interacting with registry, one additional opportunity, just a simple example would be interacting with remote registry using the service control manager versus using a WMI class standard regprov. We would be able to accomplish the same goal using both of these options. But as it pertains to .NET, we have some additional options for how we can control this flow of execution. One of which, the first that we'll talk about, is app domain manager injection. So before we talk about like how to do app domain manager injection, it's important to define just what an app domain is, like what are we injecting. So from a high level, it's a .NET feature which provides an isolation boundary for things like reliability, security, versioning, and unloading of assemblies. So basically, it provides us the ability to execute multiple applications within a single process. And if you do pen testing or red teaming and you've ever made use of projects that do inline reflective execution of .NET applications, then it probably uses app domain manager injection. If you've heard of execute assembly, basically that, but injecting into your own process. Most of the popular tools that implement those techniques make use of app domain manager injection. So we've defined app domains, but what is an app domain manager? Well, it's the .NET class that's exposed that allows you to create these new app domains. And typically the target assembly that you're loading into a new app domain needs to either exist in the same application, the same directory as the host application. This isn't always the case. There's some like hacky workarounds for that, but generally speaking, or it needs to exist in the global assembly cache or the GAC. And we'll talk about what that means and how it pertains to us here in a few slides. So if you want to do some app domain manager injection, this is what an incredibly straightforward example would look like. You just inherit the app domain manager class, instantiate this, or you create this method, initialize new domain, and in this proof of concept, all we're doing is spawning a message box. So you can create, now we've defined what an app domain is, how you interact with app domains using the app domain manager, but now we need a way to coerce the loading of this arbitrary code that we want to introduce into a trusted process. There are several ways that we can do this. Probably the most popular way to do this is using .NET configuration files, where when you launch a .NET application, the CLR by default will look for a configuration file that can consist of a ton of different attributes, two of which that we're interested in are the app domain manager assembly and the app domain manager type. So we can use these configuration files that any .NET application will look for when the process is launched to coerce the loading of this arbitrary like DLL dependency, for example. You can also do this with environment variables. There's a few more, there's extra considerations associated with this because kind of like the chicken and the egg problem, if you're using this for the case of initial access, you can't modify environment variables before you have code execution. So it would work better for like seeded access, persistence, lateral movement, things of that nature. This is not a new technique at all. It's been covered in depth, and one of my favorite talks relevant to this technique was by Casey Smith at DerbyCon in 2019 called How to Win Friends and Influence the Loader. There's a recording of that talk if you're interested in this, like manipulating .NET CLR related topics. I would highly recommend watching that. And common telemetry used to track new applications loaded into app domains. A popular way to track that is ETW. And there's a couple ways you can get around this from a user mode perspective. The canonical example would be patching the ETW event write function within NTDLL, but there's a less commonly discussed method to do the same thing, which is taking advantage of that same .NET configuration file that we're starting to talk about. And there's an attribute that you can use called ETW enable. It's documented on MSDN, and you just set this to false, and then the process will no longer have ETW user mode ETW telemetry. So let's look at quickly look at a simple example of using or abusing this app domain manager injection to achieve some sort of arbitrary code execution within a signed and trusted process. And it doesn't really matter like what process we're doing this demonstration with, because that's the beauty of this particular technique, is that it can kind of be applied ubiquitously across almost whatever .NET application that you want to. But here we're using a like Logitech binary, because this is just one that I had installed on one of my Windows machines. And the important pieces here are that we're looking at the valid code signing signature associated with it. And you'll notice that this exe.config file already exists with the legitimate application. This is that .NET config file that we talked about. Some other important things, you'll notice it's dropped in dnspy. We can see the architecture, the target framework version, some important metadata associated with this assembly. So, like the example I gave a second ago, we're just going to write a couple simple lines of C#. We're, again, inheriting that app domain manager injection class. Here, we're just doing a p invoke to call message box, say, like, just spawn a message box, like show that we achieved some sort of code execution. And then that .exe.config file, it already existed because the application used it for legitimate purposes. All we're doing is adding those two attributes that I mentioned to point towards the DLL that we're compiling that was on the last slide. Just a couple lines of C#. This is called trustworthy library, and then the name of the class. So just by modifying that config file, compiling a few lines of C# and setting them next to each other, so we're doing that traditional side load, we can see that we've achieved some sort of arbitrary code execution in the context of a signed process, because we didn't have to modify the host assembly. So all of the associated reputation will still have that benefit as it pertains to our code execution. So a quick recap of App Domain Manager injection. What's our practical use case here? Like I just mentioned, we can use it to kind of more ubiquitously sideload signed .NET applications. And it also allows us to recycle our malicious code execution. So let's say we come up with some sort of loader with all of the features, like how we want to do shellcode injection, all of that. Well, we can kind of like mix and match it with host assemblies, because all we have to do is write a .NET configuration file, and then another .NET assembly will load it. So we've defined some terms as it pertains to sideloading and hijacking. And we introduced the concept of App Domain Manager injection as one additional feature that .NET Framework affords us to execute our code in the context of a signed or trusted process. But there's plenty of other ways that we can do that as well. Another one would just be backdooring existing .NET dependencies. So before we dig into kind of decompiling some of these dependencies, first want to talk about the CLR from a high level. So when you compile C# or .NET assemblies in general, like Matt and Jack mentioned this morning, it will be represented in some sort of like IL. In the case of C#, it'll be Microsoft Intermediate Language, or MSIL. And then that will be just in time compiled before execution. So the decompilation can get you closer to true source representation of the original code, compared to like if you're reversing like C++ or Golang or Rust. A .NET assembly has not yet been compiled into machine code. It's in this intermediary representation. And popular .NET decompilers, several of which have already been mentioned today, can yield more approachable results for this reverse engineering that we're about to do. It might not always be entirely accurate. Mileage may vary depending on the tool that you're using. There's some issues associated with popular decompilers, but generally, if you check out, dnspy, ilspy.peek, a few of these have already been mentioned today, mixing and matching can get you to the results that you need. So now we're talking about backdooring existing dependencies of a .NET application. So like we find a target process that we want to sideload. It has some DLLs that it needs. We start dropping these in dnspy. But before we get to that point, we need to find kind of a more efficient way of identifying .NET assemblies to like help us reach our end goal of executing some sort of arbitrary code in a more trusted context. So lots of ways we can do this. If you just drag and drop an assembly into dnspy or ilspy, for example, if it decompiles, it's .NET. So that's a little bit more of a manual approach, but if you want to kind of start automating this, you can use PowerShell, something as simple as looping through specific directories or even your entire file system and doing a call to like assembly.load. If it errors, it's probably not .NET. If it doesn't error, it's probably .NET. But even more so, one of Steven's projects, Assembly Hunter, includes a ton of incredibly useful options that are relevant to much more than just this specific topic, but will very efficiently allow you to triage your local file system, see what's .NET, and also identify other very useful attributes about applications that you might want to target, like is it signed, is it an EV code signing certificate, information about the embedded manifest for the application, and help you figure out a lot of this useful information quickly. So when we're picking out an assembly that we want to target, what are some of the questions that we need answered, and what are some of the questions that we want answered? So it's really going to depend on your use case, like the target environment. Do you have access to third-party software that's already installed on the machines? If not, then maybe targeting like popular bloatware, something that might already have some sort of reputation in the environment that you're targeting. Is the target app.NET? We just talked about that. What is the target architecture of the application? This will be relevant to like, how are you going to, like, what shellcode are you injecting? How are you injecting it? A lot of like post-exploitation decisions that you'll have to make. Excuse me. What is the target version of, what is the version of the .NET framework that's being targeted by the application? So this can be relevant in terms of backwards compatibility, as well as are any of the existing dependencies loaded from outside the GAC? And again, we'll talk about the GAC in a second. And then some questions that we want answered, information about the code signing certificate, for example, like is it authentic code? Is it an EV code signing certificate? Because if it's EV, then it'll afford us additional benefits such as immediate smart screen reputation, which could be very beneficial in the case of initial access. And other behavioral information about the application. So like, does it make network connections? So does the EDR on the machine expect that process to make network connections? So an approach that we've taken to finding new .NET applications would just be like setting up a like Windows test VM, taking a snapshot, installing every bloatware you can possibly think of, and then using something like Assembly Hunter or a simple for loop of PowerShell doing assembly.load, find all of the .NET software that's installed, and then start this kind of manual triage process. So I spent an evening doing this probably a year and a half ago and quickly came up with like 4 gigs worth of .NET software installed on a couple personal machines. And then this supplied us with a repository of like, we've been using these for building our payloads for probably 2 years, and we haven't used all of them yet. So it can be a pretty quick process. So we've defined how we would find potential target applications, kind of what the first steps in this process would look like. But what is our objective when we find something that meets our prerequisites? So we want to hijack the execution flow of the target assembly. In the last example, we did that with app domain manager injection. It was pretty easy because all we needed was to set that config file next to the assembly. But if we want to backdoor an existing dependency, we kind of need to understand the flow of execution a little bit better to figure out where we can place our like malicious code execution and also not modify or not break the code signature associated with the host application or the host process. So this will involve identifying third-party dependencies for the target application, decompile those, and really all I mean is drag it and drop it in dnspy or ilspy, and you pretty much get the source code for it. And then find a code path early on in execution that's making use of an exported function, because remember, we don't want to modify the host assembly in any way because there's a code signing signature associated with it, reputation, and we want to use that to our advantage to potentially, hopefully not get prevented or detected. And then backdoor that exported functionality in the dependency. So I mentioned a couple times we can't just target any DLL. It's set any DLL next to the application that we want to sideload in some way. Because one instance of not being able to do this would be if the dependency exists in the .NET Global Assembly Cache, or the GAC. Basically, this is a machine-wide code cache of assemblies used by the CLR. This is one example of a directory some of the .NET GAC-related assemblies exist in. There's a few others that they can exist in as well. But the primary purpose of the Global Assembly Cache is versioning, security, and optimization of .NET processes and assemblies. Why is the GAC important? Because it affects our dependency load order, and remember, we're trying to sideload some sort of arbitrary dependency into a process, so it alters our attack surface. This is an example of a process loading something from the CLR rather than our current directory. So I set a couple DLLs next to a .NET process that I'm launching. You'll see here in the bottom left that it's still not loading it bottom right, that it's still not loading it from our current directory. It's loading it from one of the locations for the GAC. So we've talked about some of the steps associated with how we want to target some sort of existing dependency for a .NET application. Now we're going to step through a simple example of backdooring one. So just one that I picked for this was Git-related assemblies signed and distributed by Microsoft. Some of the metadata is it's 64-bit, so that's good for us from like a red team or pen test perspective. A lot of our post-exploitation tools are 64-bit, so if we're reflectively injecting those, we want our process to be 64-bit as well. It's targeting .NET Framework version 4.7.2, so for backwards compatibility, that checks another box, and it's signed by Microsoft, so that's a big perk in terms of reputation. So we dropped it in dnspy again. We're looking at some similar information. It's got a valid code signing cert. There's the assembly targeting 64-bit, and it's the .NET Framework version is 4.7.2. In this presentation, we don't talk too much about .NET strong naming, but it is something that's still relevant to what opportunities we have for sideloading .NET assemblies. And here, without getting into the internals of .NET strong naming too much, we can quickly identify a couple dependencies of this assembly that have a public key token value of null, which quickly allows us to identify that they're not strongly named. So that could, in certain circumstances, make it easier to successfully sideload these dependencies. So up here in the top left, we just right-click the assembly that we've dropped in dnspy and say go to entry point. So it's like where the flow of execution will start. And we see some namespaces that might identify that some of the code in that class points to a third-party dependency. And then we just step down through the first couple lines of code, and we see this register command from the helper application class. And something that's also important here is you'll notice references to, where is it? Right. Oh, right here. The argument length. So it's doing a check for how many arguments is expected once it reaches this portion of code execution, or in the flow of execution. So that'll be relevant here in a second. So we set some breakpoints just to validate our assumptions. And as I'm launching this application in dnspy, I provide an argument because it's doing that check for argument length. And we can validate that code path will only be reached if we provide an argument, which is beneficial in certain circumstances for sideloading. And then we step into the function and we validate that it actually does exist in that third-party dependency. So dnspy allows us to just modify this intermediate representation of the assembly. We can just add a simple print statement and a long sleep and validate that when we execute, again, that signed process, because we haven't modified the host assembly in any way, and provide an argument, because remember, when you're stepping down through the code path, you only reach this portion of the code. When you provide a command line argument, we see that we achieve some sort of arbitrary code execution in the context of this signed process. So kind of a recap of backdooring existing dependencies. We talked about .NET and how that's represented in this like IL or intermediate representation rather than machine code, for example. How the GAC is relevant to our attack surface of what we can sideload. And we made very brief mention of strong naming as it pertains to like what our attack surface is for sideloading. So we have talked about identifying ideal .NET applications for sideloading, and we've gone over two kind of unique techniques at like app domain manager injection versus backdooring dependencies that already exist. So now we're going to go through some of the other pieces that are relevant to like writing the components for the payload that you want to deliver for whatever your context is. So I'm going to kind of skim over shellcode injection, but from a super high level, for typical shellcode injection for payloads that you would want to deliver, it would be optionally opening a handle to, or if you're doing remote process injection, allocating some sort of memory for your position-independent shellcode, using something like virtual alloc, for example. Then you would copy that shellcode into allocated memory, and then trigger execution somehow, like with create thread, for example. Here are two pretty simple examples in C# and C++. The C# example here, you'll notice, is making a API call to create remote thread. So this is remote process injection, and this is just doing injecting in the inline in the process that's executing this code. And before I jump into the OPSEC notes associated with this, I mentioned at the beginning of the talk that when we make sure that we're checking all of these boxes as we're creating our payload, we don't need to do anything incredibly complicated or niche or specialized for things like shellcode injection, because when we take advantage of the reputation associated with signed and trusted assemblies, especially assemblies that already exist in your target environment, then we're afforded significantly more leniency with like how we do shellcode injection, for example. There are still a lot of OPSEC considerations associated with shellcode injection. So there's user mode hooking. I'm not going to go too much into user mode hooking other than that it's one feature associated with some detections, but it's not like the source of truth. There's been a lot of focus put on user mode hooking, I think, in the last like 2-3 years or so. But there's a lot of other telemetry that are used by security products to hook some of these API calls that you could make for things like shellcode injection. Remote versus local injection is a really big one. The majority of our injection, whether it's for a payload or for post-exploitation, almost entirely takes place in process. I think there are some relatively reliable ways to get away with remote shellcode injection right now, but it's a constantly moving target. It's significantly easier to identify because it happens legitimately less often. So sticking to inline shellcode injection or injecting into your own process is typically we have better results with doing that. AMZ is relevant. So in the case of shellcode injection, if you're generating position-independent shellcode for a .NET assembly, for example, this would still be relevant because you're loading the CLR depending on how that shellcode's injected. AMZ would be relevant. Your memory protections. So are you allocating are you allocating and executing memory as RWX or read, write, execute, or are you changing these permissions as you're doing your allocation and your copies? As well as in-memory scanning. So depending on how you go about your injection, for example, could potentially trigger in-memory scanning of your process. A couple examples would be suspicious call stacks, like remote process injection would be one that is not seen very often, or not taking into consideration the memory protections associated with like your allocations. So we've talked about how we want to sideload our .NET assembly. We've talked about the first important piece that takes place in most of at least our payloads, which would be shellcode injection. There's a couple other important things along the way as well, one of which is what I generically refer to as runtime protections, but is also sometimes conflated with the term sandbox evasion. But why are runtime protections important? Because when you're writing your payload, you often don't want to just jump into like the malicious thing that you're doing. So you want other things to happen first, one of which could be, for example, a runtime protection. And Detections can very non-holistically be broken up into two categories, static or dynamic. And a couple examples, static would be like AMZ, arbitrary strings, things of that nature. Dynamic would be like more behavioral, like heuristics that are happening post-execution. And that would be relevant to where you'd want to apply a runtime protection. Obfuscation can be our friend for things like static detections, but for runtime protections, for dynamic detections, applying something that happens at runtime will be more advantageous. So a couple friends and myself refer to where this is relevant as bad boy points. So like the imaginary threshold of crossing some boundary, like you've done enough malicious things to trigger something, some sort of alert, some sort of prevention. And there's a lot of activity that could be associated with crossing this boundary, and it changes obviously from security product to security product. And also, these vendors don't want us to know what adds to that threshold because that's the benefit for them. And the thing that makes it harder for us is that it's typically a black box. But some important attributes would be like what Win32 APIs are you using? Has the PE been seen before? Has it been seen locally? Has it been seen across like the fleet for that security product? Does the application make network connections? We talked about that already. And oftentimes, from a red team or a pen test perspective, we have to make a best guess regarding a lot of these decisions. So prior experience on detection can be changed based on like ML models per environment. So if you're detected by like CrowdStrike Falcon in one environment, you might not be in another, and that's because of what happens in the environment locally. But we want to use as much legitimate behavior as cover as we're making these decisions. So a couple examples of runtime protection, like implementing some of this, would be that the canonical example would just be doing a check for the domain that the machine that you're executing on is joined to. But there's a lot of other, you can get as creative as you want with it, and there's great repos that just have limitless amounts of runtime protections that you can implement. One that I'm really fond of in the case of what we refer to as seeded access, or when you start an engagement as like the customer will execute the payload and you start with access to the network, would be some sort of user interaction. So this is like generating, in this case, we generate a SHA-256 hash of a random phrase, and then when we start the engagement, this is to kind of prevent automated analysis or make automated analysis a little bit harder, not necessarily prevent it, but they have to enter the phrase of that, the hashed value is embedded in the payload, and it will match when the string is entered. Another really popular one, more so for like initial access, because what I just mentioned in the last slide wouldn't necessarily work for initial access, would be something that's computationally expensive. So like prime factorization, for example, just have something that takes a long time to calculate before you do like shellcode injection, for example. So the hindering manual inspection should be a goal, but not the goal. With enough time and resources, like we've had a couple talks relevant to reversing today, like several of the guys here in the audience are going to be able to write a signature for whatever payload is written with enough time. But it doesn't mean that we shouldn't increase the barrier to entry, because it makes things a little bit harder, and that might be all that we need. We all take the path of least resistance, and an important thing to remember is that a fully reversed understanding of the malicious code that you're writing is not required to create some sort of signature, so we just want to make it a little bit harder. And with that in mind, knowing that some sort of signature will likely at some point be created for the payload that you're writing, modularizing the components of these payloads is incredibly important, because you want to increase the longevity of what you're writing as much as you can. So if it's self-contained, everything most often that's needed for analysis will be in an oversimplified example in that single PE file. But if we modularize what we're writing, we can make things like shellcode injection, our runtime protections, our obfuscation, some of these important components. We can make those decisions at build time, or we can just have it be unique per build and make it significantly harder to at least write brittle detections for the payloads that we're writing. So what are some of the things that we would want to modularize? Well, the .NET application config file that we talked about for app domain manager injection, our shellcode injection logic would be an important one if you have some sort of inclination for what works better against one security product versus another, as well as the shellcode that we'll be adding to the payload itself. So we can step through a simple example of, and this will be for like where we're choosing to store the shellcode for a payload that we're writing. So instead of storing a huge obfuscated or encrypted byte array in an assembly, whether it's a DLL or exe file, we often choose to hide the shellcode elsewhere to reduce entropy. One simple example would be just appending it to some sort of image file. So all I've done here is taken an image file. I've added a delimiter of a specific 10 or 16 bytes. A specific byte will be our delimiter for where the shellcode will be. And then I just add the shellcode after that. This is just you'll notice here in the bottom right, it's the shellcode here is clear text, but when we actually apply this in practice, it'll be obfuscated or encrypted in some way. And then within our payload, we'll just include some logic to find that byte sequence, do the decryption or deobfuscation, and then afterwards, ultimately inject the shellcode. So we pretty much have the sky's the limit for where you hide the shellcode. Generally, our preference would be to just not do that in the PE because entropy is very relevant. Like if we have a bunch of mangled data, that's going to be an indicator in and of itself. So we don't want that to be in our PE. And then you also want to take into consideration like whatever your context is. In initial access, you won't be able to do things like alternate data streams because when you apply an ADS to a file, that won't exist when you move it to another Windows machine, for example. So a couple compilation considerations. When you're compiling .NET, optimizations are the core purpose is for more efficiency with whatever is being just-in-time compiled. So this will be relevant for, like we talked about, runtime protections a couple slides ago. If we're doing things like computationally expensive actions, that's something that the compiler wants to optimize as much as possible. So that's something we need to consider when we're writing our payloads. We want to make sure that what we've compiled hasn't been optimized away. Also, dead code would be relevant. So when I say dead code, I basically mean all of the legitimate code in what we're sideloading. We want that to be there. We don't want to obfuscate that because like it's not malicious and it's giving our malicious code some sort of additional cover. So speaking of entropy and obfuscation, instead of just talking about obfuscation in general, we're going to focus on entropy conscious obfuscation. So entropy is often interpreted as some degree of disorder or randomness in data, but we can make some sort of rough estimate regarding the entropy of an assembly, for example, by making use of lossless compression. So if we just compress, if we pick a specific algorithm using 7-zip or something else, as long as it's lossless, if we compress an assembly, we can see roughly by comparing when different assemblies are compressed, the like ratio of entropy. So we see we've only obfuscated a piece of this assembly, and we see what it compresses down to, and we've obfuscated the entire assembly over here, and we can see that it compresses down to a slightly larger file size, so entropy is a little bit higher. Why do we care? Because we're running short on time. The TLDR here is because most of the security vendors care. But we can, depending on your obfuscator of choice, I'm going to use Confuser X as an example, we can scope down our obfuscation. So here's an example that the code here isn't really relevant, but using Confuser X, we can specify portions of the target assembly that we want to obfuscate. You can see here that we've mangled a large portion of the code in this class, but all the other classes are left untouched, like the dead code, the legitimate code that exists in the assembly. So that's another potential indicator. If we just obfuscate the entire assembly, like all of the legitimate code, for example, then another potential indicator for our payload. And lastly, after we've taken care of our injection, our runtime protections, our now more targeted obfuscation. We want to automate all this because it can be an incredibly manual process. So ideally, the output would be like turnkey. We just say, here's my shellcode. Give me something that won't be prevented when I execute it. And so what do we want to automate? It'll be most of the pieces that we've talked about up to this point. So runtime protection, injection, things like that. And here's some code snippets. That's an example of obfuscating and choosing what type of injection that we're going to use. And then here's an example of output of what the script might look like. So like we saw in the example before, this is the output of the runtime protection. So as some closing thoughts, documentation when you're creating your specific payload implementations, documentation will be important. I know when I've written a payload, like 3 weeks later, I don't remember anything about the context for that specific .NET application, so documentation is important. And there's some really good talks about automating this process. And lastly, just kind of as an overview of the entire talk, when we make use of existing signed, trusted .NET assemblies, it gives us additional cover for some sort of code execution for initial access, persistence, things of that nature. We can customize each step. All of those detection opportunities can be modularized, so we can kind of mix and match them at build time. Being mindful of how or when we obfuscate is important. And lastly, hopefully we can wrap up all these steps, automate, and deploy them. And with that, I will pass it back over.
Thanks a lot, Nick. We will take time just for one single question, if there is one. Here. Mike is coming.
Thank you for the talk. Have you ever considered, as an obfuscation of, let's say, the IL code, to use the latest ahead-of-time compilation of .NET app, and how that will prevent some of the sideload operations that you have highlight here as a developer to protect our application?
You said what type of the ahead-of-time
compilation of the latest .NET. I think it came with the 7th version.
No, that's a good question. I will say a lot of the like sideloading and hijacking that we do is typically pertains to .NET Framework for mostly operational reasons, because most like offensive tools are written in Framework. So when we have to reflectively load them, it will need to be in a .NET Framework process. But that's a great question. I haven't looked much into it.
Thank you.